Okay, this video I want to talk about the triangle proportionality theorem. So first I'm just going to draw a triangle. I don't know why it is, but it seems like every triangle I just draw looks isosceles or equilateral or something like that. Of course this probably isn't, but it looks kind of close. Okay, so what we're going to do, pick a random point, and then we're going to construct a segment through that point that's parallel to segment AB. And the way we do that, of course, is by copying angle A. And we'll call this point D right here. So we'll copy angle A on a point D. Point the end of the compass at A. Make your mark. Point the end on D. Make your mark. Then measure the width of that mark. The compass. And then you're going to transfer that to right there. Okay, so segment DE should be parallel to segment AB. Now what we want to do is we want to compare the different ratios. We want to compare CD to DA, these two segments. And we want to compare that with CE to EB. Now let's measure CD. It looks like it's 5.0 centimeters. And then from D to A, .4 centimeters. Now why am I using centimeters? Well, it's a lot easier than using inches. With inches you have to deal with fractions and it's divided into 16ths. It's much more complicated. Centimeters is by 10, so it's very easy to measure and work with the decimals. So it looks like CE is 5.6 centimeters. And then EB is 4 centimeters. Now let's compare these ratios and see what they are. I got 1.47 here for 5.0 divided by 3.4. And 5.6 divided by 4 is 1.4. Okay, so these are very close, 1.47 and 1.4, let's say 0. Off by a few hundredths. But what this does illustrate is if I was able to draw this perfectly and there was no human error, these ratios would be exact. And that's what the triangle proportionality theorem says, is that if you draw a segment through a triangle that is parallel to one of the sides of the triangle, it divides the other two sides proportionally. So I draw parallel segment DE, that means CD and DA have the same ratio as CE and EB.